Welcome to pipingstress.net, the only YouTube channel that explains piping stress engineering with animated videos. Today, we will show you one of the methods of modeling an air cooler on Caesar 2, and we will also make an analysis as an example. Before we proceed, we would like you to subscribe to our channel, and if you think it is a helpful video, please push the like button. You can also be a member of our channel to see special videos. Air coolers are also called air-cooled heat exchangers. Air coolers are one of the most critical equipment in the industry. They reduce the temperature of the fluid with the help of the air, and a second fluid is not required. This can reduce operational and investment costs. You can watch our earlier video that explains the air cooler and its applications. The video is available in the description below, and you can also check the cards in the top right corner. Before conducting the piping stress analysis of an air cooler, a piping stress engineer must first gather certain details about the air cooler by reviewing the manufacturer's data sheet or consulting the manufacturer directly. These details include the type of air cooler, its dimensions, operating and design temperatures, weight, support type, restraint details, and whether a sliding pad is used. Once these details are obtained, we can begin modeling in Caesar 2. Let's review the technical details of our example. The type of air cooler in our case is an induced draft and double-pass air cooler. The size of the cooler is 3 meters wide and 6 meters long. The operation temperature is the average of the inlet and outlet temperatures. In this example, the inlet operating temperature is 250 degrees Celsius, and the outlet temperature is 150 degrees Celsius. So, the average temperature is 200 degrees Celsius. Looking at the data sheet, the weight of each cooler is 5,000 kilograms. This includes the header and the bundles. Finally, let's look at the support and restraints. As you can see, the cooler is fixed longitudinally and guided with 10 mm gaps. Now, let's look at the piping specifications. The input line is 6 inches, and the operation temperature is 250 degrees Celsius. The pipe material is carbon steel, and the operating temperature is 20 bar. The only difference between the inlet and outlet piping is temperature. The operating temperature of the outlet line is 250 degrees Celsius. Now, we have all the required information to model the air cooler and connected piping on Caesar 2. It is better to start modeling the system on Caesar 2 by following the fluid flow. Accordingly, we start the modeling from the inlet piping. After the completion, we assign a C-node connected anchor at the nozzles. This will enable us to visualize the forces and moments acting on the nozzles. A C-node connected anchor can be done by adding a restraint and assigning a C-node with an anchor type support. It is essential to note that the following item must begin with the already assigned C-node. Before we proceed with the modeling in Caesar 2, please subscribe and click the like button. We will now model the air cooler as a rigid member. For this, we should divide the total weight by 2. This is because we accumulate the air cooler on the edges. By this, the weight on the header side will be 2,500 kilograms. To enhance the accuracy of weight distribution, we need to divide the air cooler into sections and assign a weight to each section. As you can see, we divide the air cooler header from the center lines of the nozzles. For each section, we will share the weight. The larger section is between the nozzle centerlines. Therefore, we assign half the weight of the air cooler to section number 1, which is 1,250 kilograms. Then, the rest of each section will share the remaining weight. Once we prepare a rigid model on Caesar 2, it is important to note that the weight input should be done on the bottom parts. For the remaining parts, we can set the weight section to either 0 or 1 Newton only. As you can see, the bottom parts of the rigid item's weight are already shared, as mentioned. Now, it is time to support the air cooler. Once we look at the data sheet of the air cooler, it is fixed by the header in the Z direction. It is important to note that as we accumulate the air cooler on the edges, we should hold the rotation of the header around the X direction. This will help us to liken the real condition. Then, we will continue to model the outlet piping. Examining the pipe supports on the inlet piping reveals that the supporting principle is to liken the piping to the temperature behavior of the air cooler. The trunnion elevation is the same elevation as the air cooler support. This will help the piping to behave at operating conditions with the air cooler. The other vertical trunnion is guided in both directions. The reason for this is keeping the main line in the middle of both air coolers before cascading. This will also help the symmetrical piping approach for air coolers. Piping designers prefer symmetrical designs for air coolers to ensure even fluid distribution. Examining the outlet piping, the same principle has been applied to the support structures. The vertical trunnion holds the cascaded piping at the center of the air coolers. The output report of this study highlights several key points that warrant further examination. The primary objective is to evaluate the air cooler's performance under both operating and design conditions. As we mentioned earlier in this video, the header of the air cooler is guided with 10 mm gaps on each side. We need to see if the expansion of the cooler has reached the 10 mm limit. The other key point is the nozzle loads. The output report will show the nozzle loads that need to be compared with the allowable nozzle loads. API 661 highlights the allowable nozzle loads, which we can compare with the outputs from Caesar 2. Manufacturers often list nozzle loads on data sheets or arrangement drawings for air coolers. In the following video, we will run this analysis, review the output values, and make any necessary revisions to the piping. Thanks for watching. If you liked the video, please push the like button and subscribe to our channel. You can also become a member to get access to exclusive videos.